We present Point2Mesh, a technique for reconstructing a surface mesh from an input point cloud. Starting with an input point cloud and an initial deformable mesh, we iteratively deform the mesh to shrink wrap the input point cloud, resulting in a watertight mesh reconstruction. Reconstructing a surface mesh from a point cloud is a challenging and ill-defined problem. The central question is how to define a prior to help guide the reconstruction to a desirable result. Traditional methods reconstruct the surface by predefining some type of smoothness prior. In this work, we present the use of a neural self-prior for reconstruction. The prior is learned automatically from a single input point cloud, which leverages the self-similarity present within a single shape. Defining a reliable prior is particularly challenging, especially in non-ideal conditions where, for example, normals are inconsistently oriented, parts are missing or sparsely sampled, or the data is noisy. Using a traditional smoothness prior leads to a result which is inconsistent with the character of the global shape, whereas the self-prior in Point2Mesh inherently leverages local geometric repetitions to reconstruct a plausible shape surface. The self-prior is defined automatically by optimizing the network weights on the input point cloud. In other words, the network learns convolutional weights which directly predict vertex displacements such that the mesh will shrink wrap the input point cloud. To best explain the input object, the shared CNN weights must leverage the self-similarity present in natural shapes by aggregating local attributes specific to the entire reconstructed shape. On the one hand, convolutions are applied locally to extract salient features. On the other, the same local kernels are utilized over the whole shape. Optimizing kernel weights globally across the entire shape inherently encourages local-scale geometric self-repetition across the shape surface. Since Point2Mesh essentially encodes the entire shape into the parameters of the CNN, it leverages the representational power of networks to inherently remove noise and outliers. Accordingly, this powerful self-prior excels at modeling natural shapes, preserving sharp detail while eliminating noise.